So here is a brief summary of what you have just learned, and before we proceed, let us recall the most important points. So the Schrödinger equation for the harmonic oscillator can be written in the dimensionless and slightly reparameterized form, and we achieved that by changing the position variable to y, which is dimensionless, and using the following ansatz for the wave function psi. And now we're dealing with function phi of y. And this equation is much more convenient because, first of all, it's all dimensionless, and second, that it has only linear coefficients in independent variable. And now, from the previous discussion, you know that if energy is parameterized like that, then for the potential which is everywhere proportional to x squared, the wave functions which are normalized are described by n integer from 0 to plus infinity. So just to remind you, as long as you are dealing with potential which is proportional to x squared for all x, then n equals 0, 1, etc. But now let us consider a bit more complicated problem, and in particular let us consider the ground state, but of potential which is slightly modified. Before we discuss this modification, recall that for the ground state wave function, which is localized in this potential, it looks like the following bell-shaped function, and in fact it's localized on the length scale, which is determined by square root of h bar over m omega. And imagine that at distances, so this is our original potential, and imagine that at distances which are much larger, let's now introduce a new parameter L, and assuming that L is much larger than square root of h bar over m omega, we have now not x squared potential, but instead impenetrable infinite wall, which goes up to infinity. And we will ask ourselves a question: how will the ground state energy be modified by such change in the potential? So obviously this change will be small. In fact, we can guess that as long as this L capital is larger than typical length at which the particle is localized, then the effects of the wall will be small, as particle effectively spends not so much time in the region of the potential where the wall is located. So we expect that this change is small. So in other words, consider again the ground state wave function. We expect that the value of the wave function at the location of the wall is small. So we expect that energy will be quite close to the old one. And for example, ground state energy in the potential which is not modified was just h bar omega over 2, because n, corresponding quantized n, was equal to 0. But now we expect that n will be not equal to 0 anymore, but will still be small. And imagine we want to study exact value of n. And in the end, we could be motivated by evaluation of the derivative of the ground state energy. Let us call this f, which is derivative of the ground state energy of the particle over L. So in other words, imagine we created some box with infinitely high walls, and want to study how exactly the energy of the particle which lives in this kind of in that shaped box, how does the energy of the ground state depends on the size of the box. And this dependence will be described by the derivative of the ground state energy over L. So to summarize, the problem which we are going to solve is the derivative of the ground state energy in such potential over size of the box under conditions that walls are far from the middle of the potential. So and this is the problem which we are going to solve now. And in order to solve it, we will make use of the contour integral representation of solution of that equation. So let's go on.